Hello. Today's video is going to be about linear quadratic optimal control. There are plenty of videos about this topic on YouTube, but what I want to do is show some examples that are not shown on YouTube. First thing I want to do is I want to explain how to use an integrator with linear quadratic control. I also want to give an example of a tracking application. Instead of just having a regulator where you're controlling to zero, this is going to follow a target position, velocity, and acceleration. So I have a motion example. And the third thing I wanted to talk about, which isn't talked about on these other videos, is how do you set the parameters for Q? So let's get started. First, I want to define my system, and my controller is going to be a PID with a second derivative gain, and you will see why there's a second derivative gain in just a moment. My open loop plant is this. It's a linearized hydraulic system or hydraulic actuator. Basically, it's a second order system with a damping factor, natural frequency, and a gain. This S integrates velocity to position, so overall my open loop system is a third order system. This is my closed loop transfer function. I don't use this till I get around to plotting the Bode plot and finding out the poles and zeros, but I just wanted to show it here. To begin with, I also assign some values for the actuator gain. The actuator gain is 10 millimeters per second per percent control output. I have a natural frequency of 10 hertz, which is a little bit lower than most systems, but I've seen it as low as 2 hertz. And a damping factor of 1/3 or 0.333. For hydraulic actuators, they are generally in the range of 0.3 to 0.4. I've seen it lower and I've seen it higher. So now we're going to compute the linear quadratic gains. And first I want to show how to use the integrator. Now, if we were doing just a second order system, then what I would need to do is just use a 2x2 matrix and have these elements in here. These come from the denominator of the open loop system right here. And if we were just doing a velocity simulation, this would be fine. But I'm doing a position system, so I need to add another row and column. And what this is doing is it's integrating the velocity errors to get position errors. And then since I want to add an integrator to my controller, I need to add yet another row and column. And what that will do is that it will add I need to add another row and column for integrating position errors. This is position error row here to sum of position errors. So basically I have the sum of position errors, the position errors, the velocity errors, and the acceleration errors. And this is the continuous array. The examples I have seen on the internet, they have arrays within arrays, but I think they make it way too complicated. And there's, if you're just looking at symbols, I find that it's hard for a student or an engineer to understand what's being shown. But here I show why, and I have numbers over here so you can do your own calculations and verify your results. The B array, or input coupling array, is this. This is the numerator of the open loop transfer function. Pretty simple. I'm assuming I have a 1 millisecond update rate, which is fairly standard for hydraulic systems. And I have an identity matrix of 4x4. Now, since I have the sum of errors here, position errors, velocity errors, and acceleration errors, I'm going to have 4 gains. So this is why I have an I, a KI, a KP, a KD, and a K2, or you could say a K acceleration if you wanted to. So now let's convert the continuous time arrays to discrete, and that's what I'm doing here. There's a EXPM function, or in MATLAB, I think that there's other functions that will do this calculation for you. MathCAD does not have this capability, so I had to write my own little functions, but now it's just a matter of copy and paste. So now let's get to calculating the PID gains. Now what we're trying to do is minimize a cost function. So we have a state x, which is our actual position, velocity, and acceleration. We have a Q array, and this, these are actually sum of errors. So this is sum of errors, sum of position errors, velocity errors, and acceleration errors. Now, normally what happens is that they just assume that all this is going to 0, but my x is actually a target position minus a actual position, or target state minus an actual state. So this is the Q array, which I want to talk about in a moment. Okay, I have x, so this is basically x squared times this Q. I'm going to have the control output, and it's multiplied by a cost function for the control output, and that's basically squared. And then we're integrating it over a period of time to minimize the cost function. To do this, I'm going to do the iteration, well, 10 seconds worth. I think it'll be about 10,000 iterations. I don't think I need to do that many. What will happen is that when at the first iteration, the gains are going to be very low, and then what they do is they get to some steady state after a period of time. So this just makes sure I get to a steady state. I can probably do it in 5 seconds also. Now let's talk about the Q function, because this is what people don't talk about in their other videos. Since this is the sum of errors, since the sum of errors is going to grow pretty quickly, but the gain is multiplied by t. I'm dividing by t. In other words, in the PID, if I have ki times t times the sum of errors, I need to, what I'm doing is I'm dividing by t to normalize that, so this is the sum of errors. Then this is the coefficient for the position errors and the coefficient for the velocity errors. And again, this has to be multiplied by t, because normally the velocity errors are much bigger and the acceleration errors are bigger yet, so I'm multiplying this by t squared. So if my t is 1 millisecond, this is going to be 10 to the minus 6th. Now, why did I pick these coefficients? Well, these coefficients are almost like placing poles. Not quite, because the optimizing routine kind of changes the values a bit, but I got these coefficients from the integrated absolute error or the integrated time absolute error, I forget which one. But if you think of this as a polynomial, with this as being s to the third power, s to the second power, s to the first power, and s to the 0 power, you can kind of find the poles, or think of it finding the poles, and they're going to be complex in this case. And you'll get a underdamped response, or you'll see that the poles they're complex poles in the response. I'll get back to this later because I've got different examples here. The cost function. I have to have some sort of cost function. If I make this too small, the system will or may become unstable. Now, usually if I do the calculations and I'm assuming that I've got a perfect system, I find that I don't get an unstable system, but that's not realistic, and I'll show you in just a moment. This does the iterations. It's doing, and I think it's 10,000 iterations, and it ends up with a K. You can see that I have gains. This is my Ki gain, Kp, Kd, and my K2 or acceleration gain. And if I make this smaller, let's see if I can make this smaller. You can see the gains go up quite a bit. So I went up from 350 to about 540. If I make this a 0, it goes up even more. But like I said, it might not always be stable. So how do I know that? Well, unlike the books, what I like to do is simulate modeling errors. In other words, I've done all these calculations assuming that k is equal to 10, the damping factor is equal to 0.333, and the natural frequency is equal to 2 pi times 10 hertz, which is 58 or 62.8 radians. And what I like to do is modify this so that the system that I'm controlling is not exactly the one that I identified, which is what I call the perfect system. Now, in this example, I got positions, velocities, and accelerations. So again, this comes from the open loop denominator. I have to have an extra row and column here for integrating position to velocity. And then this is the input coupling array. And again, this comes from the numerator. So this is the denominator, and this is the numerator. I have to, again, convert this to a digital format. And then I execute the PID. This is standard updating the state. This is the PD and the second derivative gain. R is a target position, velocity, and acceleration, and X is the actual target actual position, actual velocity, actual acceleration. So this is an error. So I find out part of the output for the PID, and then this part takes care of the integrator. The T here makes it so I don't have to worry about changing Ki as a function of the sample rate. This is the error between the target position and actual position. And then this just handles the integrator windup, which doesn't occur. So what I end up returning is the new state, the total control output, and then the integrator state. So I'm starting out with the states being equal to 0. I'm going to do a simulation for 2 seconds. I'm using cosine ramps for my target generator. This is the loop I'm going to execute 2,000 times. I'm moving to 1,000 millimeters in 2 seconds in this example. And this is the result. You can see it's quite nice. Let's just move this up here a bit. Okay, now let me explain what we're looking at. This is the target position, and it's moving, or the actual position. The red is the actual position, the blue is the target position. And you can't see the light blue because the actual position is written on the graph after the target position, and the two lines happen to be identical, which means we're tracking very, very accurately, and that's what's desired. The light green is the total control output, and the integrator is the dark green line is the integrator's contribution to the control output. And you can see the integrator lags by a little bit, but you can see that the tracking here is pretty near perfect, and it is robust. If I hit Control F9 on my MathCAD, I can update or redo the simulation, and you will see that these gains can change. And since I'm changing the parameters with a standard deviation of 10, they can change quite a bit. Or let's see, 0.1, so that's 10%. So let me just hit this a few times. You can see this went from 10 to 9.56. This is a little bit low, this is a little bit low, but it's still tracking almost perfectly. Let's do this again, just so that you can see. Here you can see the gain has dropped almost 10%. And then the damping factor is much lower than 0.333, but yet it still tracks perfectly. So let's look at the target actual, the target and actual velocity and acceleration for this one example. And you can see there's two lines here. You can see there's a little bit of difference right there. That's the target and actual velocity, and this is the target and actual acceleration. And you can see the tracking is really very good. So for reasonable values for the cost functions, you can get some very good tracking. If I find the bandwidth, you can see the bandwidth is 72 hertz. This is the closed loop transfer function from above. And all I'm doing is I'm looking for the magnitude to be equal to 0.707, which is what it is, and I find that it's 72 hertz, and the error is very, very small. So this is the Bode plot, and you can see it's very flat. And because there's 3 zeros and 4 poles, you're going to have a final phase delay of 90 degrees at the very end. But you can see that the magnitude is really very, very, very flat. Now let's look at the poles and zeros. Okay. You can see that, well, it's one pole you can't find on the plot. Let me just show you where they are. One pole is at minus 358 radians, but the other poles are at 29 something, so or at least the real parts are. So you can see the 3 real poles, I mean, they're not real, these are 2 complex ones. And you can see the zeros are very close to the poles, which almost cancels them out, but it makes it so that effectively there's just that one pole that's way out on the negative real axis. So that's why the response is fairly good, and because these poles are away from the imaginary axis here, you know the system's going to be stable. So let's try making some changes here just to see what happens. First thing, why don't I make the cost function smaller? I'm going to make it 0. And like I said, for the most part, the system is stable, even with 0. But that's assuming that I'm using the same parameters to simulate the system that I use to calculate the PID gains. So what's going to happen here is that sometimes you're going to see a stable response, and other times you're going to see a, well, the system's going to go crazy. So let's just take a look here. And let me do a Control F9. Oops, it did it the first time out. Okay, so basically what I'm trying to get at is that if you make the cost function small, these gains will be big, and the chances are the control output will do, you know, even though it looks like it's tracking, it's not going to work in real life. So you need to have something for a cost function here. If I make this a 0.1, which is much greater than the 0.005, it reduces the gains quite a bit. Doesn't seem to change the control output. You can see the light blue peek out from below the red just a little bit. And this doesn't track quite as well either. Get that to stop. You can see there's some difference between the target and actual acceleration. But still, you can have an awful lot of leeway on how you change this cost function for the control output. So let's go back to 005. Oh, let's do one more thing. Let's just make this huge. You can see the gains are very low, and it's not going to track well at all. See that? So let's go back to 0.005, which is just good enough to keep it from oscillating. Oops, not that. Down here. 0.005. Now, I could probably go to 0.01, or I could have a wide range and it still probably work. Now let's talk about the Q matrix again. As you can see, because there's a time relationship between the sum of squared, the sum of errors, the velocity, and the acceleration, I have scaled these coefficients accordingly. But I can also change these coefficients. If I choose this, in theory, the poles, well, they're approaching real axis, or they're going to be approaching the real axis. And let's just look down here, but you can see it's not quite. Response still looks pretty good. You can see that they're getting closer and closer to the real axis. If you look at polynomial 1, 3, 3, 1, you would have you should have 3 real poles, but because of the calculations that it does, it's keeping the zeros close to the poles, and they're approaching the real axis. Now let's pick something where we know it's going to be real. Oops. Where did it go? Let's go over here. Now, this should have 3 real poles. Oops, wrong one. Okay, now 1, 4, 4, 1, a polynomial of 1, 4, 4, 4, 1 will have 4 real poles. And if we go down here, you can see there's 3 real poles, plus there's a 4th one way off to the left on the negative real axis at minus 341. Now, if we take a look at the response, it's still very flat. Let's take a look at the bandwidth. It dropped down from 74 to 73, which is not bad. Let's take a look at, well, I guess we've seen everything so far. Oh, I guess we can look at the plots. I'll go back up. And you can see that the response is very, very good. So, what I have done is I've shown you how to add the integrator for the controller. I've shown you how to choose Q, what is involved in choosing proper values for Q. I have shown you how to change, or the effect of changing R, which is the cost function. And I have shown you about the parameters, the coefficients, and how that affects where your closed loop poles are going to be. So that concludes my video. Hope you find it useful. Bye.